some sense that something is going on, that they better run to high places, and those survive. So we lost something. We may have had it, but we lost that sense, and we need to have sensors that we can build that could help us do what these guys are able to. And we lost something like 200,000 people at that time. Something simple like the woodpecker. It knocks on wood. Try to knock your head on the wall and see what happens. You get dizzy, and this woodpecker does it for living. That's how they get food. That's how they build their nest. The people who hold the jackhammer, everything in their body shakes. If they have dentures that is loose, it flies from their mouth. The woodpecker doesn't have that. So what made nature so capable? Well, it's the biggest lab ever existed and ever exists, because there's a lot of trial and error, and the only thing that work last and continue to other generations. And of course, it's inspired a lot of things, and this workshop is about that too. And there is an incredible pool of invention that nature came up with, that why reinvent the wheel? Just sit there and try to understand what it is and try to copy it. I'm sure we have seen a lot of examples even in this workshop, but as simple as honeycomb. It's used in every airplane, not to store honey, but because it is lightweight and strong structure. Something else that was copied, things like the body armor. You know, look at the turtle. And of course, the turtle is very slow, and so does the knight with their clothing. But we did, as humans, we take things that just improve them all the time. And today we're using this technology, we call it technology, in a tank. Now they have GPS and all this technology we have, and make it comfortable to sit inside the tank and use it. And of course, flying, we saw a lot of, as humans, we've seen a lot of insects flying, a lot of birds flying. And it didn't see, even though it seemed like it is so easy to do for them, wasn't easy for humans, because people tried to copy that. Just copy didn't work until we did our homework. We learned all the tools and whatever, and now we can fly. And we beat nature in no time. There's no bird that can fly this fast, no bird that can fly that high and carry this mass, and on and on and on. And simple engineer, we have this spider. It's marvelous. It built this web that is just incredibly flat, and can just be impressed with what it can do. Of course, there is a lot of other things that are good challenges. Performance of the hummingbird and the dragonfly, and there are people who are trying to copy it. There's a group not too far from our place in Pasadena that made a little hummingbird that can fly and send videos to a control station. But we also have other things that we tried in terms of flying, in vision of using electroactive polymers, which is going to be some of the focus of my talk, using it to flap, basically create a plastic wing that flies in different planets. And we have the thing that is called, basically it's an airfoil called wingsuit, that people just jump from high places and, wherever they hit. But, the early developers, none of them died old. And you can imagine why. Talking about things that would be nice if we can copy, the octopus is incredible. I heard the word talk about that too here, but it's incredible, but it has things that we already copied. Suction cups, in bathrooms and, in windows. This is a good way to stick things. So with tentacles like that and a suction cup like that, you're on the grip, it's almost impossible to get out. But look at what the octopus can do that you may be impressed of. What it is doing, you will not be able to do it. Look what it did. It took all its body, squeezed it to a narrow opening, tube, and just got to the other side. There's nothing that is robotic and with solid structure that will do this trick. There's another trick that the octopus is able to do. There's an octopus in this picture, huge octopus. And it is hidden so well because of the camouflage capability that, you know, you don't see it. Look what happened when it noticed that it is on camera. Look at that. If you were a fish, this is your last day. And what is amazing about this creature, it is colorblind. It is able to copy everything, the color, the shape, the texture. I was trying to imagine to myself, if I had this capability, how could I tell even what is behind me? You know, that alone, having all this resolution and all this capability, it's amazing. Now we're thinking of the chameleon and the octopus as capable of making ability to camouflage. Camouflage is used by nature almost everywhere, including plants. We don't think of plants as camouflaging. Let me show you what they do. I noticed that by the way, there's a book coming in 2 weeks that this is in the introduction chapter. I noticed I have a lemon tree. And lemon, what is interesting, the fruit stays long time on the tree. And here I was taking a picture of the fruits, and here's what you notice. Look at what happened. This is the ripe fruit, right? We know the code, color code, and this is not. When it is green, you don't eat. When it is yellow, you eat. This is what nature coded its fruits. Most fruits are green. And guess why? Simple. They don't want you to see it. It's too early. Once it's ready, they give it smell, they give it color, they give it everything it can. Taste, whatever, so you will eat it, because it's ready. Another thing interesting, it's important that the flower will be visible. Very important. So what it does, some trees shake the leaves. So the first thing that comes out is the flower, not the leaves. The flower comes out as big as it can be. This is magnolia in my front yard. And once they are ready to become fruits, guess what happened? Those leaves are not needed anymore of the flowers, and now we have the real leaves. And then what is interesting, if you notice, most of those fruits are even hidden behind green leaves. And you can see some of that. Okay? So camouflage is plants do other things too. We don't think of plants as even moving. They have muscles-like capability. Some of these plants, this fly trap, a fly goes in, that's it. The door closes, and now it's food. It has also the pitcher plant, same thing. Closed door, now food is ready. There is also the fern that when you touch the leaves, they close. It's quite fast, relatively speaking. Roots of trees are powerful. They can lift curbs, they can lift building structures. This is how powerful they are. So we don't think of plants as capable of doing motion and forces here. And of course, this gives us ideas for biomimetics. The tumbleweed inspired a vehicle for Mars. The idea is to have like a beach ball. There is a lot of wind on Mars. The atmosphere is not that high, so it is not that much forces. But you're talking about something like hundreds of our atmosphere. It is only 6 door as opposed to 760. But the wind speed is about 24 kilometers per hour. Decent. So it can move a beach ball like that. It has a total mode. There's a hole in the middle. So once it reaches a place where we want to do sampling, Sampler comes down, takes samples, analyzer inside, do the analysis, and basically it does what the rovers are doing. Moving on to the more sophisticated capabilities that we're looking into, we have legged robots, like the one that was shown on Monday, the big dog, they're incredibly capable. This one is developed at JPL for 6 legs, and this is one that I was working on years back, and the idea was to use it as a platform with suction cups to walk on airplanes and carry instruments to inspect and do whatever maintenance needed. More specifically, you're familiar with the Mars rover. We're going to send another one. The new one that's going to be launched in November is called MSL, Mars Science Lab. They may have another name by the time it is launched. And it is as huge as a car, weigh about a ton. And when it arrives to Mars in March next year, it will be different than what you've seen before. There will be a rocket that brings a lander close to the surface, and out of that, the rover will come down with cables, just like a spider. It will come down with cables. Once it hits the floor, the rover will be released, the cables will go away, and the lander will just be launched to whatever happens as long as it's away from where the rover is. Exciting, sounds science fiction, but that's what it is. Hopefully in the future we'll have walking robots. And the reason is we are finding more and more areas like this as opposed to a nice flat area. Also, we have one of the rovers that was, since 2003, got stuck in the dunes, and I have an illustration of it, where one leg, the only one, one wheel outside the sand, which is the only wheel that doesn't work, the rest digged itself into the soil, and now it is so dug in, covered with sand that it's not working anymore. But after 7 years, with a plan to use it only for 3 months, it's not bad. But when you look at what these guys are doing, the mountain goat, look at it. This guy is already resting up there, enjoying the view, and this one is going to get there. We don't have a vehicle that can do this trick. We're trying to make one. This is one that I'm working with another roboticist at JPL that we're looking at making one, and we made all the required foundations, including a drill that basically does not require much force to push into a rock, so that it basically grip itself as it goes up on mountains like that. That brings us a little bit closer to the subject of human-like robot, because it's the most sophisticated capability. When I was young, this used to be the robots that we imagined, and basically it was a machine that walked like a toy. And of course, now we are more visionary. Adi Marom is the girl that is the artist who made a lot of the arts that I'm going to show. It was part of a book that I published in 2009. And the idea is that we will have eventually something looking like us that basically will do things that we do or better. And the question is, what does it take to make that? We need some intelligence, and this is the robot that Ira mentioned. I took this picture at Johnson Space Center. It's a duplicate of what we have now on the space station. This robot basically can sort mail. It takes an envelope and does it. It was built as a telepresence, which means that someone an operator wear a suit that has sensors, and the robot basically image those actions of the person. But now they're making it into autonomous. So effectively, the possibilities of making a robot smart, there are 3. One is to keep the intelligence to the human and make the robot totally dumb, but just copy whatever the human does. This is one possibility. The other one is to make the robot totally autonomous and have it smart, but we are far from having our wisdom in it. This now goes into that mode of becoming as smart as possible. Eventually, I don't know when that's going to happen, but eventually this robot is going to be demonstrated, or at least tested, for plugging and unplugging, things that we think of simple for human to do, but for a robot, it's a big deal. Turn knobs on and off, and things like that. Strapping, unstrapping. And there is a whole scenario of things that everything works without damaging anything they will do with this robot. And of course, the ultimate is if we are starting to make prosthetics for human, hands that looking very much like human hand and so on, eventually there could be situations where someone who has deteriorating body but able mind could be having a whole body implant where the brain is the only thing that represents the person. Could be. And now you have a totally smart robot because it has a human brain. Okay? Sounds science fiction for now. Now, why? We have to ask that question. Why do we need to do that? What's wrong with a robot like R2-D2, from the Star Wars movies? It has a, like a barrel shape with half sphere on the top that turn like the head. What's wrong with that? We are very comfortable. I mean, most of our world is built around our size. The handle. You come to the room, it's not here, it's not here, it's here. So it will be comfortable. The chairs we sit on, everything around our world is built for our comfort and our size. So might as well, if you have a robot, might as well make it our size. So it will be effective. Because if you want a robot for your grandma, getting old, she wants to have help, and she doesn't want to go to a nursery home, and she wants to enjoy herself in her own home, it would be nice to have a robot like that. Now, why does it have to speak like us? We are very comfortable with verbal communication and facial expressions. We understand that very well, and you don't want to have grandma sit down and type, I want food, and by the time she types it, she's already starving because she makes mistakes and whatever the robot interprets. We want a simple communication. And increasingly, if you notice, the interfacing with machines are done as simple as possible. You take an iPhone, and you can do with your fingers what you really want. This is what I want, this is what I want, and you do this, and it's expanded. Everything is more intuitive, and as much as possible, communicative. Okay? So we have an example here of a hand holding and a robot I'm going to show later. Where did it start? Humans, as soon as they were able to move things, even if it was the marionette with wires, they started making robots, ideas of dolls that you can move with wires. But we have Da Vinci made a design of what is called a robot. He was working with a lot of human muscles and whatever, and he designed something that he never tested. But someone about 60 years back in England went and just basically, whatever he was able to interpret from the drawings, he made the mechanism, and it does work. If you pull on the wires, effectively the equivalent of muscles, it does work. The earliest equivalent of a robot that we know has been in the 1700s. The most famous one is this Reiter. It is still in a museum in Switzerland. And I got this picture from the museum where they have that, and the condition there was that I'll give them 2 free copies of the book, which is easy. This robot, there is video on the internet, you can see it in performance. It has this feather, and when it dips the feather into ink, the eyes watching the ink, it shakes it, all driven with a spring mechanism and gears, and it can write up to 40 characters, which is incredible for those days. And the amazing thing, it still works. And the name of the person who made it is a watchmaker, and this company, I guess, it still exists.
Well, you know, actually, every first Sunday of the month at 12 o'clock, they're being demonstrated. There's three of them.
Oh, really? You know that?
I've seen them. And a drawer, and then you have an organ player.
Oh, there is also a flute player. There is few famous ones from that period.
They demonstrated all three of them.
Oh, really?
At the same time, yeah.
Oh, wow. Have you seen it?
Yeah, and the writer is actually programmable. You can program the text it writes.
Right. It has gears that you can change fonts.
Yeah.
This is amazing for those years. Right. You're talking about, you know, look at when was it? You know, 250 years or so? It's amazing. But this is what they had in those days. That brings us to our days, and you know, in writing the book with David Hanson, who is also a roboticist, I came up with this idea of having a figure that represents human like robot. Because if I make it totally looking human, it's hard to say, yeah, this is a robot. So we chose the body to look machine, and the head to look human. You probably have seen this head before. It's David from Michelangelo statue that we turned it a little bit color so it will look human. But there is a lot of aspects to, and this week we heard some, and you're going to hear more, about things that make a robot like that feasible, possible, and operational. I'm going to focus more on what it takes to make the muscles, which is really the weakness we have today. It's still not there, unfortunately. Now, electroactive polymers that we call artificial muscles, their response, or characteristic of the response, is the closest to look like our muscles. The first person, I published a book in 2001 about that, and I was looking, you know, if you publish a book on the subject that's supposed to cover everything, I was looking to see the history of how did it happen. And what I found was that Röntgen, the guy who came up with the X-ray, did one more thing that he just didn't know he did. He took a rubber band and hanged on it a mass, clamped it with 2 electrodes, and he saw movement. But he didn't realize he was the first to do EAP. He thought it's a thermal effect, so he dropped it, but he reported it. He had a paper in German that he published here. Dan Sakadot did some modeling, so he's the first theoretician who played with polymers. And then you can see that the milestones are 30 years later, 50 years later, and it only in the 90s where things started moving significantly. The amazing thing to say, or give credit for, in Japan, in the middle of the 80s to the 90s, they had a major program to look into this material. Most of the work they have done was with gel polymers. And, but everything was Japan only kind of thing. You know, the only spin-off that came out was some workshop. There was one workshop that included something like 20 people worldwide who knew about each other in the beginning of the 90s. Okay, but PVDF, which is well known, came in the end of almost 1970. Not everything is electroactive, not every polymer. And there are others, and I thought to mention that while we're talking. And some activity is not necessarily mechanical. There is photoactive. There is also what we call smart structures, people using shape memory alloys and all other kind of materials to create active of some sort. Also, there are deformable polymers, like the McKibben muscle. It's just a balloon that inflates and it has threaded cloth on it. That when it expands, it shrinks in the length, just like when we do like that. It's never been used in prosthetics because it's too noisy and slow, because there is a pumping air in and out. It's things like working on laser, but that is on a small scale where you shine laser and it should contract or expand. There is polymers that are called shape memory, where you squeeze a polymer under heat and pressure, and then when you hit it back, it goes and expands, and it can go something like 40 times the size because it's foamy structure. That brings us to the EAP. I'm an expert in ultrasonics. And at some point in the beginning of the 90s, I decided, why don't I expand beyond ultrasonics? And I started looking into the ideas in smart structures. And a chemist in my building came to me, and I saw an article about PMMA, which is plexiglass, basically, with different toxicities. And this report of two groups from Germany and Japan wrote that they have a electrostrictive effect in these polymers that reaches forces of our hands and strain of 15%, 14.7. So the article, my gosh, incredible. So I wrote a proposal to NASA to develop artificial muscles. I got the money, I got $1 million, 3 years. Sure enough, started working, and they made big mistake. 10 over minus 5 orders of magnitude mistake. Nothing moves. And I worked with really top-notch guys from NASA Langley who are chemists who know they could not reproduce the results. Tried to contact those guys to find out, am I wrong or they are wrong? And found they were wrong. They realized that, but they didn't want to admit it. It was very difficult to reach them. And basically, I was on my own. I had $1 million, I have nothing to use. Luckily, around that time, materials did start showing up. And one of them is the electric EAP, that's called the electric elastomer. You hear about that more and more. And was made by a group in near San Francisco called SRI International. And another one was this material, ionic polymer, IPMC it's known. And it also appeared around 92 by, just amazing, at the same time, group in Japan, New Mexico, and another individuals who no one knows where he is now. But the other two were still around. So I started working with it, and at least I had something to work with. And when, at NASA, when you get a contract, every year you have to show success. Luckily, when I made the proposal, I said, I'm going to show 10% contraction, but nothing about force, luckily. So at the end of the year, I said, the bad news is, the paper that everything was supposed to be based on, wrong. The good news is I managed to get something that contract 11%. So I exceeded 10% more than I said I will, and I'm a hero. So they gave me, after I worked on this, they gave me another 2 years, added another $500 million, so it was nice. So what I started initially to do, I'm not a chemist, and I realized that if we want to draw people into this field this is very multidisciplinary, it is important that all this long description of chemistry, what it is made of, or the name poly something, is too complicated for people to appreciate or know what it means. So instead, if I can categorize those materials, it would be easier to deal with. So I came up with this distinction. Initially, I called one group ionic, the other electronic, because one is driven by ions moving in diffusion, the other one, electrons moving inside. But the electronic may be confusing because people thinking of it as an electronic device, so we started using more the field activated rather than. Now the distinction is this is contribution of chemist, it's chemistry in action, and this other group is physicist. It's just physics in action. This group requires really low voltage. Something like 1 volt would drive this material in this group. The other one, enormous voltage. You're talking about something like 100 volt per micron, which means if you take your hair and try to drive it, if it is EAP, you need 1,000 volts. So a lot of people are scared to hear, voltage like that being around, but the advantage is it doesn't require much of current. After all, this is insulator, those are plastic. So basically, this is the two groups, and no other distinction created so far, so it seems like everyone agree that this is a good division. And what we see here is the kind of names of materials that are around. I also see it as a marathon race where these materials are trying to somehow go from novelty of something exciting that moves into something you find in every store, in every instrument, in every whatever. So it seems like in this race so far, that the electric elastomer is the winner. But the reality is it's not exactly what we call electroactive in the sense that it's active inside, because the material itself is actually mostly passive. It's more the force that drive or the electrostatic forces that makes it move. If you have two electrodes and they have polarity of opposing polarity, they attract each other and they squeeze the material to become wider and thinner. Okay? To see some information about it, why we get excited about these materials, what is exciting is the strain that they generate. If you look at the top list of strains, electroactive polymers, the group at SRI have demonstrated something like almost 300% strain, surface area strain. They have a famous disk on a rubber disk of electrodes, and this squeezes and expands. Shape memory, they generate high strain of 8%, but you don't want to use that because if you take a metal and bend it, they break in no time, so they try to keep them below 4%. And the last one is the electroactive ceramic. Those are not so friendly to strain. So they are used in the range of that you see. There are some that reach closer to 1%, but the majority are below that. In terms of force, this one has the highest force. This is the lowest and sub-medium level. So you have the numbers, you can see them. What is exciting about this material, the polymers, are that they are lightweight. For space, it's important because, we're trying to save mass. The heavier something, the more it takes energy to bring it to space. And of course, the bigger thing about them, they are resilient. You can do things like what I'm doing with my hand, freely moving. Some more accurate numbers or more detailed numbers you can see here. I'm not going to go over the details in short time. You can find it in the literature. But let's see how it looks like when it moves. Here's an example. And this specific one is IPMC. Everything is immersed in water. And you see it moving, and it looks alive. This is, of course, not a tweezer. This is electrodes. They're holding it. And this is like starfish. It looks alive. Find me another material that does that. The next one next to it is a ferroelectric EAP, basically like a piezo. And the way it was made to bend like that is to use what we call bimorph. Taking a film that is active, bond it to passive, and when one stretches, it creates bending effect. Otherwise, it just... Now, most of the ionic type are made to bend, as opposed to the ones that are what we call the electronic ones. Here's some examples of those, and if you remember, I mentioned what SRI have done. This is what they have done. See it in action, it's really impressive. And here is other example. Someone from Korea even took those tapes that have metal on one side, glued two of them, so the metal served as an electrode, and he showed that they have, electroactive effect to some extent. The EAPs that we are seeing here or at least the electronic one, all of them stretch. The contraction is in the thickness, because you need to have as thin as possible material so you can get the electric field that is needed. So in order to get contraction, different people came up with different ideas. One is Federico, he spoke here last week. He came up with this idea of folding a set of strips to create contraction because the thickness contract, okay? And someone from a group in Switzerland, from EMPA, Gabor is one of the lead researchers there, they just took thin films and they created a stack, which those who are familiar with piezo, that's what they do in piezoelectric material. They create stacks. But as opposed to piezos, that is much easier to create those thin films uniformly and so on, this is much harder. And they're trying to make a machine that will make this uniform, and they're still having issues. But I've seen a demonstration. It's impressive that it's able to contract and to lift significant mass. I'm not going to go through the details, but as you can imagine, we don't have one winner material that has everything and it's perfect and we don't have to worry. Everything has advantages and disadvantages, and we need to know what principles. So when I say EAP, it's not just one material. We have to be specific about what it is. But having disadvantages is not a disaster. You know, it's important to know, if you're an engineer, if you don't know the disadvantages, you design and you will fail because you didn't know. But here's an example. Electricity. If you take a nail and stick it into one of the plugs, one of them will kill you. That doesn't make it bad. If you are careful, if you know how to avoid, you take all the safety precautions that is needed, and you don't do something stupid like that, then you enjoy all these things that electricity give us. Same thing about EAP. Some of them, if you prepare them, this is chemistry. When you prepare them, you have to be careful and take it into account. So you need to know the disadvantages. I'm going to show a summary of those tables. So this is just intended to show that there is a lot of information about it. And here is the ionic polymer. Again, a whole list. But just in summary, so you'll have an idea of what kind of advantages. So what we call the electronic or electric field activated, the advantage is they operate dry. So you don't have to worry about operating them in room temperature, in room conditions. They are fast. They are faster than the ionic. They are operating up to 1 kilohertz. If you put them in DC, they hold the position. We cannot do that. This is not a DC for us, because sooner or later I will be tired. I don't know, there are motorcycles that have the hands like that. I don't know if you've seen them. I don't know how they last like that, but they do it. It is something you need to, this is important for robotics. If I put the position like that, I don't have to feed it with power. It stays there, okay? And it creates large force. So if you need large force, this is the way to go. However, there are issues. The voltage is high, and there is no magic around it. Maybe the idea, that's what EMPA is trying to do by using thin layers. This way, that's how you reduce the voltage. And that's what they do in piezo, as I mentioned. They require compromise of force and strain. If you have high strain, you can get to compromise to get more force and so on, so you can balance. Glass transition, it's an issue when you go to low temperatures. And it's a problem with all polymers. You know, it's low temperatures, it's an issue. And they mostly produce, this is also an issue, but you could deal with it. They mostly produce one polarity because it's related to the voltage square. So no matter what voltage you use, it's always bend in the same direction. So something you need to take into account. The ionic, they create mostly bending displacement. It doesn't have that much of the torque or bending force. The advantage is it requires low voltage, something at 1 volt. You can drive them with a simple battery. And they are bidirectional. But the weaknesses are Most of them do not hold position. This is chemistry in action. DC create movement of ions. So keep moving. So you put it under DC and they can do things like that, you know, fold on themselves and so on. Slow response. You know, the bending is a low force, and let's see if there is anything. And operating in air is a big deal. They dry in air. And when I started working with it, I used to get material from New Mexico, and at one time I went to show it as a demo at a review, internal review at JPL. It worked when I left the lab. Trying to check it before I am supposed to make the presentation, it doesn't move. At that time, I realized I have to take that into account, and I didn't think about it. I'm not a chemist. You know, here you give a material, you think of it as a mechanical device. So that's what happened. Anyway, the efficiency is also low. Okay, some examples. Once I got the funding, once I had this contract, it's important to have something useful when you bring chemistry, and I was funded by robotics, NASA robotics program. So you have to show something robotic. If you tell them that you mix this with this, no one give a, you know. So I came up with an idea of making a windshield wiper, because there was a rover, tiny rover like that was supposed to land on a comet. And the idea was to throw a detonator onto that body, and all the dust will fly, and when rover lands, it will be pristine surface, never been exposed to UV and all these bad things of meteorites and stuff, whatever thing that hit the surface. So here is a windshield wiper that I came up with. So it moves and bends, and I got excited about it. Everyone got excited, but then I started looking into specs, because if I want to design it for mission, it's important to have specs. And if you look, there is some leftover. And I asked how small this leftover can be. And I was told sub-microns. So I cannot use that simply as is. So I came up with this version that uses electric field repulsion, a brush that is made of fiberglass. Electrodes are basically coated almost to the tip and leave a gap. And with 1500 volts, dust fly because they're repelled. Okay, and you can see the dust flying. And basically, it was part of the mission. It was supposed to fly, but the mission was canceled, by the way. That's what happened. Then in parallel, I was looking at the robotic ideas, and this is a robotic idea that I came up with, because if we're starting collecting samples from planets, it will be nice to have a hand like that the films weigh 0.2 grams, and they only use 0.1 watt, which is effectively almost nothing compared to other instruments, and you can see how nice it can grab things. And I even came up with robotic hand. Here is this was IPMC, and this one is dielectric elastomer that allow you to raise and lower the arm so that it will work like a robotic arm. And this is the rover that I was talking about. It basically was supposed to serve as a windshield wiper. So following this funding from NASA, I got the funding from DARPA. And it was more looking at the whole field rather than using EEP for robotics specifically. So this is what I came up with for looking at the field as a broad topic. We have material that we knew, and we still don't have new materials since then, by the way. The only thing we have is improvement. We have the two groups, ionic and electronic. And as I said, I'm looking at it as a marathon race. And what obstacles they have to run through? Good science and engineering. So good science, we're talking about nonlinear mechanics. You're not talking about infinitesimal displacement. We want to have full displacement or big, full level. We have even characterization of the material, and the performance is a big deal. You cannot put strain gauge. strain gauge will make it not move. Something like computational chemistry need to come in place so that we can predict what materials will be there rather than mix and find out. Here's a fabrication, engineering, how to fabricate materials, how to make shape, how to coat them. All those things are problems. One of the guys made EAP from gel that expand 100%, but he was able to do this experiment once. Because what happened, the electrode fell apart. And it's funny, if you see the picture, one picture was made with a scale of centimeters, and then the other one with inches. But he couldn't repeat the experiment because it's already everything fell apart, and it took him a long time just to make this experiment. So once we have that established, even miniaturization capabilities, we can make sensors, actuators, applications, and so on. So that brings us to more details. What I showed earlier, this is the infrastructure we want. So far, not much work has been done in this area. Computational chemistry. It is just like finite element modeling for mechanical people. You can predict by putting atoms in different places, what properties it will have. And once you come up with a good choice, let's say the computer can do it, then you can find out how to synthesize, how to make a material that is not toxic or useful and so on. Also, we need good modeling, theoretical works, and there is a lot of work done. In the last over 15 years, there's a lot of things going on. I started the conference, the first conference in 1999, and since then there is so much body of work, it's unbelievable. A lot of understanding and improvement since then. And of course, fabrication, even we've been thinking of using, and there are people already using inkjet printing technology, whichever is used in printers, to create those EAPs. And it's amazing how effective this technology of inkjet. They take two streams of drops flying, and they merge and create combined drop. This is how accurate everything is. And of course, we know that because you see the marvelous pictures you can create with inkjet printer. And of course, for other aspect is, I thought of making composite, because if in metals, if you cannot get properties, you create alloys. You mix different metals and you create the properties. So here I thought that would be nice to have a mixture so that, because the issue with EAP and the reason why we need high voltage is the low dielectric constant. Most polymers have a dielectric constant below 10, and that's the problem that we have. So Kim Il-sung ended up with using such an application of mixture, and he was able to reduce the voltage by order of magnitude. So the film that I showed earlier that was showing bending in air, he made that, and I used something like 300 volts instead of 3,000 volts that was needed. Again, how do we make the measurements? We ended up using a video camera to watch the movement, and in order to create load, we hang mass at the tip of the film as it is moving. And there is a lot of properties that we have to track, because now it is not enough to look at the electrical, not enough to look at the mechanical, we also have to look at the combination of the couplings. Applications that people have been looking into included medicine. And like looking into prosthetic possibilities. In Sweden, they were looking at taking seaming veins in a surgery, microsurgery. A group in Korea were looking at a pill that can go through your digestion system and basically like a worm, just travel. Because there are pills that have camera on them that people swallow, and the camera take pictures as you go through your system. This idea was so that the doctor can also track what's going on inside the system and go up and down as needed. Also, there is some work done on Braille ideas, and mostly there is something like 9 groups worldwide. I started this idea because I saw some blind people in Washington at one time and came up with an idea of having electrodes that are like this. Strip on one side one way, strip in the other way, and you can individually address whichever pin you want by activating that individual crossing. I put it in the book at the time that I published in 2001, and since then people started moving the field forward. Just a comment while we are on the subject of Braille, Napoleon is somehow tied to it because he asked his engineering corps to develop a method of communicating at night, and one of his officers developed a 12-pin code, and they wanted to teach the soldiers to use it at night. They hated it. So they ended up taking it out of the military. They didn't want to use it, so he went to an exhibition that they had a workshop in Paris, where blind people, the principal of a school of blind high school, attended, and they talked about having his code maybe to the blind people. One of the students that was chosen was Braille. This guy Braille thought of ideas to improve by cutting from 12 to 6 pins, 2 rows of 3, and this officer felt this blind high school kid will tell me what to do. Guess what happened? This blind kid became the most famous person as opposed to this officer. So he wrote the book after he finished high school. He wrote it in his code, and of course now it is well known that he is the guy who came up with the code. Years later, they came with 8 pins instead of 4, with 4 in 2 rows. This is how they create 256 characters, which is what is needed for ASCII code. Concerns about the field? No established database. Because it is all handmade, most of it, 2 different batches, 2 different behaviors. Need to identify applications where EAP will be the only way to do. This is what is critical right now. Because if it has to compete with other technologies, we look at its weaknesses. But if this is the only way to do it, then we live with the weaknesses. And as an example, if those of you who are still remember the days of the floppy disks, they were lousy. You could lose the data in no time. But we used it because guess what? We didn't have any other alternative. It was a polymer way. It was a floppy disk, which is made of just a film. There are lifetime issues, the reliability issues, and so on, scaling issues, just on and on. Something about the forces and compare to human. When you compare the performance, here's data that John Madden from University of British Columbia prepared. And you can see that EAP sit comfortably around some of those polymers. So we have materials that can beat muscles with work density and strain performance. But, oops. Okay, how do we do this? Shoot. Okay. So that brings us to the comparison with muscles.
Considering the low actuation force of current EAPs, a challenge was posed to the science and engineering communities. The challenge is to develop an EAP actuated robotic arm capable of winning an arm wrestling match against a human opponent.
I posed this challenge when I started the conference in 1999. And you can see this is what I used to demonstrate that I get 11% strain, contraction, because it contracts as a combination. At the time I was asked, You know, when NASA announced that we're going to use it on a space mission, I became very famous. It was announced all over the news, and in one of the interviews, someone asked me, when do you think this will happen? I said, I don't know, 20, 30, 30 years. Sure enough, in 2004, things started rolling faster than I thought. First of all, I got a contact from Marvin Cohen, who is one of the directors of the movie Over the Top of Sylvester Stallone, that supposedly someone worked for a living arm wrestling. And he wanted to see the wrestling match. I said, look, we don't have a wrestling match. I set up an EAP, an action session, on the Monday of the conference where you could see the latest in the toys of what the guys are doing. But it's far from wrestling. So anyway, he asked if he can attend the conference, and I arranged for him. He came as a Fox News sport representative. And he brought with him the world champion, the California champion, and the wrist wrestling champion. And when they came, they asked me, where do we put the table? What table? Apparently they have a respectable table. I didn't even know. I thought of just doing like kids, you know. When I was young, this is what we used to do with arm wrestling. They have a very standard table, and they brought it. And then that year, just coincident, we did have volunteers that said, we will do next year an arm. Here they're listening to me, saying to the community that eventually we need to win against these guys, but for now we'll win against a high school student. And here is a high school student that I chose, a nice girl, who was a high school student. She was head of a robotic club and smart, straight A, and all this good stuff. And she wrestled at that conference. So here's what's going on here. The most famous picture is this one, because the students from Virginia Tech spent time on making the arm-looking arm. So of course this is more famous because it's a nicer picture. But they use chemistry, ionic material. That is why she's wearing goggles, because we don't want her any spill and anything hurt her. Then, this was the last one. This one was the first one. She looking happy, and eventually she won. It took her some time. She won, and it took her something like 20 seconds to win. But this one is the second that won. She won here after 4 seconds, this one after 3 seconds. Look at her. She's scared out of her mind. And look at the hands. She has a glove. You know why? When you see those cables and you are told that there is 4,000 volts running through, I don't think you will be happier than she was. This was made, by the way, by the group from EMPA. So anyway, the year afterward, there was a lot of media and everyone was excited, but the purpose is not just a circus. The purpose is scientific one. So with the group from UCLA, we made this picture that when you look at, oops, what happened here? Sorry about that. Put it in my pocket. And when you look at the picture, she's pulling on the cable. There's a mass of 0.5 kilogram here that when she lifts, so the device has to lift at least 0.5 kilogram, otherwise we don't want to waste our time. So once it reaches a straight cable, then there is a device here that measures the force. So we measure the time, how long it takes to go up, and we measure the force of pulling. The 3 arms that participated, 2 from Virginia Tech, again this arm, another one from the electric elastomer, and this one was the same one. Apparently he had used ship memory alloys in it. She won again, but at least this time we had numbers. And the numbers are 2 orders of magnitude faster and stronger than what we had in 2006. Since that time, we did not have competition. And it's really unfortunate because they have thinking of a human as the object of wrestling rather than comparing to that year. Because I prefer to do incremental improvement until we reach that point. We're not going to reach one day we're going to beat human. Hopefully that will happen, but it will take a while. In the meantime, we have quite a bit of development. The group from EMPA developed this blimp that has steering. The fins are controlled. It was a cover page of Scientific American in 2003. There is a commercial product that came in 2001 or 2 from a group in Japan. Let's see that. What it is, it's a fish in an aquarium. It costs $200 a piece. You don't need to feed it. All you need is to have water in the tank because it's rechargeable. It is actually not rechargeable, but driven by a coil inside the body of the fish, inductively fed from the top and bottom. I'm not sure how they made the buoyancy and the control, but it seemed like interesting, at least the videos that I've seen. It didn't hit anything and was comfortably swimming inside. I saw those fish. I was in Japan in a place where they did show it, and they're about this big. I tried to take a picture, and these guys are very much trained that when they see a camera, they jump in front of you and say, don't even think about it. So anyway, so here's the fish, and you cannot buy it if you're not in Japan. Here's other evolution of the development. The group from EMPA made this blimp that wagged the body. People have been doing some work with fish here. This is what these guys have done. Evolution did not develop a fish that fly like that, because none of our animals have helium in their body, but in a balloon like that, you could do that. So it wagged the body and wagged the tail, and it basically propelled itself this way. In terms of development, some data statistic that I got from GM, General Motors, that make cars, because they're looking into making use of EAP, and here is fascinating data. The purple is patents that were documented for use of piezo. What you notice is that there is saturation, and this is 2005 data. The data that I've seen, I don't have a copy of it, in 2007 showing already decline of that level, and this brownish color is the EAP, and it keeps going, and basically it's starting to go parity with piezos as much as patents coming out. What's that?
What are SMP and MR?
Okay.
You know?
SMA, shape memory alloys. SMP, shape memory polymers. MR is magnetorheological liquids. Those magnetorheological liquids, there's so much I could cover in this meeting, but they are liquid that when you subject them to magnetic field, because they have powder that's magnetic, they become viscous, very viscous. There is also electroversion, that when you subject them to electric field. All Lexus cars have this fluid in them. Incredible performance. They control the density, not the viscosity of the shock absorber using this material. So all the cars and more high-performance cars have this liquid in them. It's a fluid. That brings us back to the bigger picture of the robots. And David made this face. And it's supposed to be a platform for people who develop EAP. Because I don't believe if someone say, yeah, I have material, after having material that was claimed to be incredible muscle potential, if anyone has, here is in my lab, I have this head, and we can try and see if it works. Also, we have this robotic hand that Graham Whitley made. If you saw the picture earlier, which hold wine, he works now in a company that makes prosthetics. At the time, he was doing his PhD when he made this robotic hand. To some extent, we're thinking we are smarter than robots and we are more capable than robots. And what makes us unique is we express emotion and we can, feel emotions. Let me show you that robots do have emotions.
Nice robot. You're such a cute little robot. You're so serious.
So this is Cynthia, she's from MIT, and this is a robot that was made in 2001 or something like that. Here it is from 2002, the reference. Moving forward, now, of course, we are more capable, more sophisticated, so David Hanson made this Einstein head that is able to make facial expressions. He made it in honor of the relativity theory in 2005, and it was presented at the meeting of heads of state in Korea. I'll show it in a minute. And this robot was made, the cyber receptionist was made in Korea, in Japan. And the idea was to have a receptionist that can help you and so on. And of course, it also have facial expression. So if you don't talk nicely to it, it will start cursing you and scream at you. So that's talking about the ultimate in expressivity. So anyway, recently they started using it as a teacher. And of course, the kids are very careful with her. That's a picture of President Bush at the time, shaking the hand of our robot. And here is a video of the robot itself. And it has a body of a robot. It was made by a Korean company. That was a combination that he made the head and they made the body.
My name is Albert Einstein. I am a physicist.
And look at the facial expression when the camera zooms on. Look at it.
My name is Albert.
So he's looking at you, and at that pose, you look really live. Okay. How the field is evolving, there is two directions that they're going in. One is I distinguish between humanoid that look like human, but not exactly. Well, helmet head and body that look like human, but simplistic. Those are already coming into commercial world in Japan. This robot, they're using them in shopping centers. If the robot sees someone looking at a map, it comes, asks, may I help you? And if the person asks, where is whatever, it takes you to that store, print coupons to you, and tell you all about what the store sells, so you will be encouraged to buy things. This robot is about here big. It's incredible in terms of performance and mechanical movements. And I'm going to show it in a minute later again. But the human aspect, the human making, here's Hiroshi. He's one of the leaders in this field. Made a clone of himself as a robot. If you look carefully, you can tell that this is the robot clone. This one is from China. I took this photo when you came to LA. There was an exhibition there. And you can see the beauty of the others, and I talked already on the cyber receptionist. And here's the beauty of robots. And you can imagine the kind of application they're thinking of it. You pass in the street and someone asks you, robot lady lift the dress and you can negotiate price and all those things. This could be an successful, who knows, internet was developed in that direction initially. And all this paying through the internet was developed that way. But it's incredible beauty. Look at the one on the right. It's amazing. And of course, other areas that could be, you want to immortalize yourself, you make yourself cloned into a robot, and years later, 10 generations from now, they want to know what you were thinking. If you were faced with the same problem, if you understand at all when they're talking to you about the technology terminology in those days, but I'm sure they can get updated. Then you can have this robot. This is Philip Dick, the American science fiction author of the, Blade Runner. Go see these videos. It's incredible movies. Minority Report, Total Recall. Incredible science fiction about robots. David Hanson made this one. That brings us a little bit closer to applications of the other area. This is prosthetics made under the DARPA program. They're making prosthetics look so much like humans' hands, it's unbelievable. When you see the prosthetics of today, That brings me to the talking about that. In 2008, an athlete from South Africa wanted to compete against able human with normal human healthy legs. He was rejected by FIFA, the international committee that decide who will attend, who will not. He was rejected because they claimed that he has better performance and advantage over able people because his legs do not require so much energy as able people when they're running. He appealed this rejection, and he contacted a friend of mine in MIT, whose name is Professor Hugh Hale, who is an amputee himself. He was in an avalanche, his leg were cut, and he have now prosthetics. And he showed that it is not proven that there is advantage. They basically, the maximum we can say is that they're equal. And therefore, he was okay to participate. The reason why he did not attend is that he did not practice, he was busy with the appeal. So when he was trying to be sent from South Africa as a representative, he lost. So he didn't go to the competition. But the fact that we reached this point, that we are not even sure which one is better, that is an important milestone. An airplane beats any bird. Whatever we develop, sooner or later it will be superior to anything else. When you look at the example of those smartphones, I used to have the old stuff. The battery, as soon as it dies, you have to re-enter everything. You know, look at what it can do today. I cannot imagine what else can be done, but I imagine there's a lot of smart people thinking what to put back.
Pistorius actually participated in the World Championships just a few weeks back in Korea.
Oh, really?
Yeah, he did.
And?
Well, he didn't make it to the finals. He got into the qualifiers for the 400, and he was not selected for the 4x100 team of South Africa because he was not fast enough compared to the others. But he's competitive, sub-top, you know.
Huh?
But the problem is set.
It's amazing that we reached that point.
Sure, of course.
And everything could be just better. And we are only in 2011. Okay, but when we see the hand here, we're getting there. Other aspect is...
How are we doing time-wise? How many more slides do you have?
Oh, maybe 4 or something like that. The amazing thing is now it is connected directly to the brain. This guy, they connected to his nerve system, and he moves his hand like that. And I've seen him. He showed me eating M&M. You know what is M&M? Those tiny candies, chocolate candies. This is incredible sensitivity and resolution, ability to hold this and eat it. He was able to do that. Other prosthetics, I'm not going to go too much about it, but here's a chair that has legs climbing stairs. Some say, ideas for the future. This is, by the way, my dog, and the artist, by the way, I never seen the artist, but we communicated by email, and she created this pictures and some more stuff, ideas of having a, assistant of old elderly and going in hospitals. This is the robot I showed earlier. Sorry. But David Hanson is trying to make a toy that is dedicated to your kid. As opposed to dogs that can be nice, friendly to everyone, this one will be programmed just for one kid. So every kid has to have one. And it will talk and make facial expressions and basically very friendly and so on. And he's trying to make it below $300. Things that we have to worry about, as opposed to buying TV and you put it home and nothing happens until you turn it on and you can see things. This thing can cause trouble. And if you know Microsoft Windows, if this is programmed that way, just if someone put a virus into it and it started destroying their house, by the time you come and call someone to help you, your house is destroyed. This is possible nightmare. You don't want even to think about it. And what if they can do if they're used as soldiers? They could be, wars could start in no time because you don't have to worry about people killed. And of course, another aspect is this. They could demonstrate against us. They want human rights to human-like robots. And whatever that means, there's a lot of meanings to that. Some of the books that I can mention, this is the book that I published in 2009 with David Hanson about the human-like robot, and this book, there's one about biomimetics that came in 2005, and this one is coming this month. And that brings me to the last slide. And I have a lot of visitors to my lab, from heads of NASA centers to students. So at one time, I had 10-year-old kids who were chosen as an award to visit JPL. They visited my lab. And one of them was looking at my eyes very strangely. I didn't know why. So when everyone left, he came to me and asked me, "Are you a robot?" Yeah, it's a shocking question the first time you hear it. Now I'm a little bit more prepared for that. I said, should I pull his leg or tell him the truth? Anyway, I told him, no, I'm not a robot, but good question. You never know, 20 years from now. But just having a kid thinking I'm a robot, we are almost there. AI has been here for 50, 60 years already. It's not where we were thinking they will be. But look where we are today. We have robots that understand speech. They're robots that can recognize people. They understand speech to the level of 1,000 words. That's a lot. There are people who do not understand 1,000 words. And this is incredible capability. Slowly, we're getting used to just working with robots. When you call an operator, I don't know how it is here, but in the US, you don't talk to people. You talk to machines that understand you. You go, there are stores that you can buy by just working with a machine. You buy gas, you don't talk to people. We are going into that world. And the biggest fear of elderly is that one day, like we are when we call an operator and there is no one at the other end, it's just machine, there will be only machines around them. That is a nightmare. Hopefully it will not happen. We'll still have us somehow involved with other people. With that, I want to thank you.
Great. Thank you. Okay, wonderful. Thank you very much. Questions? Ricardo?
Well, it was just a curiosity about for space mission, it's energy consumption, the main problem that you have. So this is the main challenge for all the kind of artifacts that you have to build. Is the power consumption that will be very low.
Well, there is quite a few things that we have to worry about, including power. The power is not an issue, I would say, because it's really using low power. One of the toys that are being made now is an attachment of iPhone. It definitely have to last a little bit. And it's supposed to be working in an interface with games. So power is not an issue. The issue is, would it last in the environment we're going to? More and more we're going to an environment that our house. Future missions are going to be to places that are crazy, like Venus. Venus, we have 460 degrees centigrade, 91 atmospheres, and sulfur. So if there is hell in our neighborhood, it's probably there. And if we're sending anything, it better work in that hell. Okay? And of course, we have low temperature. Europa, Titan, we're talking about minus 180 degrees centigrade. That is almost impossible for EAP. It's not the high temperature we can handle and not the low temperature. So those are. However, there are things that we could do with EAP only, effectively. We're talking about making a big telescope that inflates in space. We already demonstrated that in 1997. But making a film like that, huge, it still have to obey optics. And you cannot afford wrinkles on the surface. So it would be nice if we can somehow stretch and make it look nice, even if we rigidize that. But it would also be nice if we can make change of focus, so we can look at this place and this place. Because Hubble is limited. It's about meter diameter. If we go beyond that, the mass is going to be 8 times because we are talking, if you just double it. So we cannot afford that kind of mass going with the glass lenses. It has to be something more lightweight.
Other questions?
Okay?
Martin?
In your introduction, you said we build humanoid robots because they can survive in the environment we build, so they can grab the same objects or they can repair stuff. Now, I read that in Fukushima, in the first 3 months, there were only 2 robots on the field. They were from the US Army. They were responsible for measuring the radioactivity. So I would like to know from you as an expert, you think we're on the wrong track? Or how could it be that a nation like Japan, which is so fancy for making robots, is not producing exactly robots that we can use for something like this? Do we produce the wrong robots? Or?
They built a wall next to the ocean of 20 meters high because they thought they know about tsunami. The water was 36 meters high, so it beat them. If it was 19, they may have saved it. Same thing with these robots. They probably thought they won't need this kind of robot. Everything you make is cost. So you have, as an engineer, you have to design per specs. If you make it too capable, it will be very expensive. No one may not pay for it if they think it's not needed. That's probably what happened. So if now that they recognize that things like that is possible, I'm sure the next thing we'll find next year is new models that can handle the conditions. It's just a requirement. If we have a requirement, someone will make it, because the technology is there.
Vicky, other questions?
There's this tendency lately to have bio-inspired, let's say, engineering. So this EAP, how close is it to something like a natural counterpart? Is it?
The EAP we have today, unfortunately, they are not where we would like them to be. It's just like in artificial intelligence. We are not where we would like to be. They can do a lot of things, but we are not where we would like to be. The 2 commercial devices that I mentioned is one is that fish, 2002, and the next one is this new attachment of iPhone. What you do with that, if any one of you familiar with the Angry Bird game, it works with it where the kids, well, the adults, hold it, and besides seeing things falling and destroyed, besides loud music of things destroyed, you also feel things falling in your hand. It makes the game quite exciting. That's what they made it. But it's a toy. It's not something serious yet, but a matter of time. Because once it's become a commercial product, people start giving feedback. People put money into it, and the profit is used to improve. This is what I'm looking to see. I would like to see more commercial products so that we will have the cycle of improvements, of money feeding in, because there's not that much funding as it used to be at the beginning where it was a novelty. Now it's more out there and whatever funding that is helping to develop it.
So I have a last question. So you give us a very visionary outlook on where we're going and sort of moving in this direction. But one reason why I'm not too worried about robot wars is that essentially robots are very much blind. They cannot plan their behavior very well. They have massive power problems, massive compute. So the robots we look at, internally it's still more like this. So we can make them look very human-like and we can anthropomorphize them as much as we want. But in terms of control, we're still here. So how are we going to take that? How are we going to solve that problem?
As I said, there is infrastructure to everything. You have pieces. We need power, we need control, we need muscles, we need appearance, we need all those other things. We have improvements all the time. There was a question I asked about power because I was concerned about it. These robots that are, they can operate up to half an hour to an hour. That's it. So if you're in a war, just wait an hour, don't do anything, and now go take them and put them in the open and recontrol them and send them against your enemy, This is what it is today. It would be nice if we can do what we do. Harvest. We go eat and we take it from our neighborhood and create food for ourselves. If we have a robot that you send it to anywhere and grab leaves and eat and grab branches and eat and just create or to whatever fruits it picks and just like us, then we don't have to worry. Because sooner or later, even us will run out of fuel. After a few hours or a few days, you'll be starving. So we have to have this ability to create our own power, but it has to be different than what we're using. And using solar is not enough. I mean, you cannot have a robot standing like that, let's say, on the end of his solar cells and wait for the power to be enough to move the next step, you know. It's not fast enough. In space, we use, to places where we have problem with power, is using nuclear sources, you know, thermal generators. But on Earth, it's not exactly, you know, a robot with nuclear sources not going to be so receptive, you know, unless the enemies will use that. But they have to worry about their own side.
So still some way to go in that sense on planet Earth.
With that?
We still have some way to go on planet Earth.
A lot of, but it's amazing how far we are. In terms of recognition, you know, we took a camera, the cameras now can recognize eyes, and this is just a simple camera. The robots recognize eyes. So when you're talking, it looks to you into your eyes, it can blink, and basically talk to you as if you're conversing with it. Okay, so it has that. It can interpret what you're saying, and it can memorize your face. So it can tell, you know, and this is the thing that David Hansen have done. You know, so you come to see the robot the next time after it asks you your name, it will remember you and say, hi, John, how you doing, and so on. And you feel more compatible. I mean, you know, it's becoming more social.
Very good. Well, on that note, thank you very much.
Thank you.